So this ramp is getting pushed up this ramp. This box is getting pushed up this ramp at a constant velocity. So it's clear which way the box is going. Friction needs to be the opposite direction. So the applied force is going to have to be up the ramp to overcome the friction, as well as overcome the gravity. So let me get set up here with my direction vectors. And now a free body diagram. Okay, so we'll have gravity straight down. Try that again, straight down. Draw the components in for that. And then we'll have a normal force that's going to cancel out the y component of gravity. So they'll be the same size, tick marks. And then I'll put friction in. Friction's going against the sliding. So it's pointing in the x direction. And then the applied force. So the applied force has got to match the friction plus the x component of gravity to have it be at constant velocity. All right, so this is my free body diagram. The normal force equals the y component of gravity, which I'm going to rewrite as mg cosine of theta. And that's the y direction. So now the x direction, the applied force is going to equal to the sum of the force of friction and the x component of gravity. So these two forces that I just wrote down are pointing in the x direction, which is down the ramp. And they're going to equal to the magnitude of the force pointing in the negative x direction, which is the applied force. Okay, so that way everything is balanced. Let's take a look at what we're asked to find here, which is the coefficient of friction. Okay, so that's going to come into play when I rewrite the friction variable as the formula mu times normal. So there's the mu that we're going to solve for. The FGX, I'll replace that with the formula for the x component, mg sine theta equals the applied force. That's just given as 115 newtons, so no need to replace that with any kind of formula. Okay, so what's going to happen is we'll isolate for mu, and that's going to look like, so F applied force, subtract the mg sine theta, that's the first step in rearranging the equation, and then divide everything by the normal force. That'll get mu isolated. So we're going to make a substitution here, two equations. Both equations have normal force in it. So I'm going to make the substitution of mg cos theta in for the normal force of the other equation. Okay, so this is going to be a large expression here. And now I will go ahead and insert the values. I can't really cancel out the mg too well in this case because only one term of the numerator has mg. So I'll just fill in the values now. So 115, take away 20 times 9.8 times sine of the angle, which is 25 degrees, divided by mg cosine 25 degrees. Okay, so let's see what that gives us. Hopefully some reasonable value. And I'm getting 0.18. Right, seems pretty good for a coefficient of kinetic friction.